Hi, welcome back everybody. This is example 10.6. Very similar, well, not very similar, but we're going to be using a lot of the same principles and the equations that we used for the last problem, the last example problem on the rotating curveball pitcher. But this is with what should look like, I think, a very familiar game show wheel that you spin around. Okay? So I'm going to start by not even really reading the question, but I'm just going to look through it and pick out some of the values that we have. An initial angular speed, I didn't mean to do that. Move it back there. An initial angular speed of 34.0 radians per second. All right, so our omega initial, did I say 34.0? I meant 3.400 radians per second. Okay? Well, that's how fast they're turning it when they first spin it. And by the way, note that it is going counterclockwise, which we consider to be the positive direction. All right. It rotates through 1 1/4 revolutions. So what would that be? So it goes all the way around one time and another quarter, which actually, I should erase that. Unfortunately for this game show person right here, 1/4 revolutions around. Let's say we start here on the far, at about 3 o'clock. That goes around one time, and then 1/4, and it stops right where the person's arrow is. So that's bad news for them, but, well, that's life. So what is that? Well, that's an angular displacement, right? So that's our delta theta. Now that is 1.25 revolutions. We need to turn that into radians, right? 1.25 revolutions into radians. And so we know that 1 revolution equals 2 pi radians. All right, so 1.25 times 2 pi. We can convert that right away, so we can use it right away later. Our delta theta is going to be 7.85. 7.85 what? Radians. 7.85 radians. All right, that's what 1.25 revolutions is. And if you think about it, 1 revolution, we say that's what, 2 pi? That's like 6.28 radians. Well, a little more than that. 1 1/4, that's going to give us up to 7.85 or close to 8. So that's going to be our angular displacement in radians. All right, comes to rest. What does that mean? That means our final angular velocity equals 0. 0 radians per second. All right, let's find the angular acceleration of the wheel that as it slows down, and let's find the amount of time that it takes. All right. Well, I can tell right now I'm going to have to shrink this down because I need more space. I'm going to put this sort of up in the right or upper left right there. Okay. So our A, angular acceleration, is what we want to solve for. We have initial angular velocity. We have our angular displacement, and we have our final angular velocity. We should be able to solve for our angular acceleration. And it should go like this. Angular velocity final squared. Now keep in mind how similar this is to our kinematics equations, or one-dimensional kinematics equations, equals initial angular velocity squared plus 2 times our acceleration, angular acceleration, times our angular displacement. All right, this was just like saying v final squared equals v initial squared plus 2 times acceleration times delta x. Well, it's exactly the same thing. It's just we need to use our angular values right here. So let's just go ahead and solve this for our alpha, our angular acceleration, and put in our values. So let's see. W. Oh darn it! I keep saying W. It's an omega final squared minus omega initial squared. And then we're going to be what? We're going to be dividing a 2 down and the delta theta down, right? That's going to give us our angular acceleration. All right? So let's just put our values in. Our final is 0. That's easy. Minus our initial angular velocity, 3.40 squared. 3.40 squared. Divided by 2 times our delta theta. That is, we had it in revolutions, but we converted it to radians, which is the real unit that we want to use. That's 7.85. 7.85 radians. That'll give us our angular acceleration. Or I should say, this is going to be a deceleration, right? What do we get? I get a total of negative 0.7. Let me try that again. Negative 0.7. I'll put a 0 out front. 0.736. What? It's radians per second squared. That is our angular acceleration, or I should say our angular deceleration for this wheel. All right, probably caused by friction because it spins on some sort of bearing, but nothing's perfect, so it probably slows down because of friction. All right, part B, let's solve for time. T is our unknown. We have initial angular velocity. We have our displacement. We've got our final angular velocity right here. You know what? We used this same equation before. Let's use a different one that involves our acceleration. All right. If you recall previously in example 5, we had time and initial velocity and displacement and final velocity. Let's use one that gets acceleration in on the action. I think we have one like this: angular velocity final equals angular velocity initial plus acceleration. I almost drew an A, and then I drew a pretty lousy alpha. Acceleration times time. Well, solving for time is going to be pretty easy. That's going to be our omega final minus our omega initial divided by our alpha. Assuming our alpha is correct down here, which I think it is. All right, that's going to be our time. So time will be our final angular velocity, 0. That's easy. Minus our initial 3.40 divided by negative 0.736 radians per second. How many seconds is that going to come out to? Negative 3.40 divided by negative 0.736. 4.62 seconds. I get 4.62 seconds. And that seems like a reasonable amount of time for it to slow down. And that's our answer. So, another example of using rotational kinematics values, but using one-dimensional or linear kinematics equations. They match up really, really well. And so get used to this, and this should come back to you pretty easily, and you shouldn't have any problems. So thanks for following along. I'll see you on the next one.